Hey, welcome back to the channel, everybody. This is Kevin, and in this week's video, we're going to talk about a very fundamental concept in networking. It's the OSI model, the Open Systems Interconnect model. In just about any introduction to networking course, you're going to hear reference to this OSI model, and a lot of people think it's a little bit boring, and honestly, I don't think it gets the treatment it deserves. There's a lot of components to this OSI model that just go overlooked and skipped over in those introductory level classes. So in this video, we want to dive a little bit deeper. Let's do a deep dive into the OSI model. And the OSI model, by the way, it's a 7-layer model, and a lot of people want to start counting at the top. Think of this as an office building where you go into the first floor and then you go up to the 7th floor. Yeah, the numbering starts at the bottom. So we say that the physical layer is layer 1. The data link layer is layer 2. The network layer is layer 3, and so on. And to memorize these layers, there's an acrostic I want to share with you. It's please do not throw sausage pizza away. The P in please reminds us of the P in physical. The D in don't reminds us of the D in data link. The N and not reminds us of the N in network, and so on. So please do not throw sausage pizza away. If you want to memorize this from the top down, you can memorize that all people seem to need data processing. And as we look at this model, our main focus in pretty much all of our networking studies, it's going to be on these bottom 4 layers. In fact, at these bottom 4 layers, we actually call data by different names. Let's talk about how we refer to data at these bottom 4 layers. And the names that we give to data, they're called PDUs, Protocol Data Units. Down at the physical layer, layer 1, data is referred to as bits. And at layer 2, data is frames. At layer 3, we call those packets or datagrams at layer 3. And finally, segments up at layer 4. So the PDUs are bits, frames, packets, segments. And as another acrostic memory aid for you, remember the acrostic bacon frying produces salivation. The B in bacon reminds us of the B in bits. The F in frying reminds us of the F in frames, and then produces salivation, packets, segments. And now that we've talked about the structure of this OSI model, let's ask ourselves, why do we care about the structure of the OSI model? Well, the OSI model is going to be a way for us to categorize just about anything happening in our network. For example, if you and I are doing troubleshooting together, I might say to you that we've got a layer 2 troubleshooting issue, so we know where to focus our efforts. We know what's happening down at layer 2. Or if I've got a physical layer problem, maybe I have a cable that has been severed, something like that. So this is a way for us to categorize protocols, devices, services that are running on our network. And the best thing I've ever heard about the OSI model is this. I read this in a book a long time ago. It said that the OSI reference model is a reference model. It's not a reverence model. We don't revere this as to say that everything in networking has to neatly plug into one and only one layer in this model. That's just not reality. Some things will span maybe 2 or 3 layers. Some applications, we might not be able to point to a session layer for that particular feature in our network. So it's not a reverence model, it's a reference model. It's a way for us to better categorize what's going on in the network. And we want to take a look in this video at what's happening at all 7 layers. And our primary focus is going to be on these bottom 4 layers. That's where we're dealing with the actual data that we're trying to get from point A to point B in our network. And let's begin down here at layer 1 with the physical layer. What is going on down at the physical layer? Well, the physical layer is concerned with how we get bits across our network, how we represent bits. Devices you might see at the physical layer could be something like your Ethernet cable. This will be a physical layer component because bits physically travel over this cable as electrical signals. Or we could use light with a fiber optic cable to send data. We might have a network interface card inside of our computer that's going to encode data so it can be sent out on the wire and it can receive data. These are examples of things, devices that might live at layer 1. Layer 1 is also concerned about how we represent data on the wire. And there are a variety of examples out there, but let's take a look at just one to give you a better sense. Let's consider a way of encoding data called AMI, alternate mark inversion. Now, AMI goes by the thesis that it's best to have an average of 0 volts on the wire. That's a good electrical characteristic. So what we're going to do is represent a binary 1 as the presence of voltage. One time it's going to be positive, the next time it's going to be negative. So on average over time, we have an average of 0 volts on the wire. Let's go to the whiteboard and take a look at this. Let's say that we have positive 5 volts, negative 5 volts, and 0 volts. And we're going to divide our time into these different time slots. We'll talk about clocking and how the sender and receiver know when one time slot starts and when the other one stops. But let's say that we want to represent some data. In this first time slot, what we can do is give maybe a positive voltage to represent a binary 1. So it's going to be a 1. And let's say in the next time slot, we want to represent a 0. So we drop down and we send 0 volts. And maybe we do that for a couple of time slots. Maybe in the next time slot, it's time to send another binary 1. But remember, we want an average of 0 volts on the wire. So what we're going to do is, since we sent a positive voltage previously, we're going to send a negative voltage. I should have made this one a bit higher. We're going to send a negative voltage. That's going to be another binary 1. And let's say that we've got a couple of binary zeros. You see what we've done here? And again, this is called AMI for alternate mark inversion. What we've done here is we've used the presence or the absence of voltage to represent binary 1s and 0s. And over time, we have an average of 0 volts on the wire. We have a positive voltage, a negative voltage, 0 volts. On average, we have 0 volts on the wire. That's a good electrical characteristic. And other things that live at layer 1 include our wiring standards and the jacks we use to plug into the wall. Let me give you a couple of examples. One jack that you hear a lot about is the RJ45 jack. Let me put that down so you can get a better view of it. The RJ45 jack is an 8-position, 8-conductor connector. And what I mean by that is the connector itself has room and has space for 8 different wires. And each of those wires can be used as conductors. But when we call it an RJ45 jack, I know I'm being overly technical here, but just to be super technical, it's really not an RJ45 connector. There is no RJ45 standard. There is an RJ45S standard, and it's not this. It looks like this, but it's got an extra little sort of a notch in it. It's a keyed connector. It's not what we think of as an RJ45 connector, but this is commonly used in the industry. I'm perfectly fine with you calling this an RJ45 connector. No worries there. But that's an example of a connector. And the way you put the wires in there, the color coding that's used, that is based on a standard. There's a standard that's commonly used called the T568B standard. And that standard says what colors of wires we put into those different slots in this connector. And something else we're concerned with at the physical layer is the physical topology of a network. Just a few examples include a bus topology, a ring topology, and a star topology. Let's take a look at a few examples. The first network I ever worked on way back in the 80s was a bus topology. Literally, we had a coaxial cable that just kind of ran from room to room to room in this office building in this particular floor. And if you wanted to get on the network, you would tap into this coaxial cable. So let's say we've got a computer here, and we've tapped into this coaxial cable, and another computer here, and we've tapped in. Maybe we've got a printer here, and this was called a bus topology. And the devices on this bus, they ran in half duplex, meaning that we could either send or receive, but not both at the same time. The reason was you could only have one packet on this wire at any one time. And as a result, we ran something called CSMA CD. Carrier sense multiple access with collision detection. What this means is before this guy can transmit data on this bus, he listens to the wire to see if the coast is clear. If he hears nothing, the assumption is that there is no data on the wire. We can only have one packet at a time, so it's going to send its packet. Now, here's the challenge. What if, let's say we've got somebody up here and she sends data on the wire and he sends data on the wire at exactly the same time because they listened to the same period of silence. If that happens, let's say that she's sending a packet down, he's sending a packet up. When those packets meet, there's going to be a collision. and a collision is going to corrupt that data, and we're going to have to retransmit. Another type of topology is a ring topology. With a ring topology, we are logically connecting to a ring. We'll talk about logical topologies in just a moment, but we're logically connecting to a ring. Let's say we've got 4 computers here, or maybe 3 computers and another printer. And the way this works is there is a packet. Let's say that she sends a packet on the network and it starts to go around in this circle. And if there's data in this packet, actually it's called a token. If there's data in this token, then when the next person gets it, they look at that token and say, oh, there's data in here. Is this for me? If it's for them, they will take the data out of the token and they'll empty the token and send the token back on the wire. You have to be in the possession of an empty token to transmit. And the token circulates around the ring, so there's no contention like we had with the bus topology. The token circulates around the ring, and that's the only way we can transmit. We have to be in possession of an empty token, and we look at those tokens to see if the data is for us. Now, this is how things logically work, but physically, we're talking about the physical layer. Physically, it looks like this. Let's go to another page. Physically, we have something that looks a little bit akin to an Ethernet switch. It's a MAL, and this means that we're going to be physically connected using a star topology. We're starring in to this centralized location. Give our printer again. So this is a physical topology. Even though logically we're passing things around the ring from device to device to device, physically it's connected like this. Now this physical topology is a star topology. There actually was a ring topology that was in pretty common use around the late 1990s, and that was something called FDDI. That was a fiber ring, actually a dual opposite rotating fiber ring, where you could send packets in both directions around 2 different rings of fiber, but that physically was a ring. So that's one of the things we define at the physical layer, the types of topologies we're dealing with. Do we have a bus? Do we have a star? Do we have a ring? As just a few examples. And something else happening here at the physical layer is synchronization. The sender and receiver need to agree on when bits start and stop. One way of doing that is to use asynchronous synchronization. With asynchronous synchronization, the sender tells the receiver, hey, I'm about to transmit data to you. And with synchronous communication, we have a clock that both the sender and the receiver reference. Yet another function of the physical layer is how we use bandwidth. There are a couple of major options. We have broadband and we have baseband. With broadband, it's sort of like your cable TV where different channels use different ranges of frequencies. So you can tune into a channel, you're tuning in to a range of frequencies. That's broadband, where we can have multiple conversations all going at the same time using different frequencies. The other option is baseband. With baseband, all the frequencies on the medium, they're used for a single conversation. And that is all defined down here at the physical layer. And something else happening here at the physical layer is multiplexing. Multiplexing defines how we send different conversations at the same time over the same media. We've already talked about one. Remember, we talked about broadband. We said with cable TV, different frequencies could have their own channel on those frequencies. That's really how wireless networks work today. We have this band of frequencies, like the 2.4 gigahertz band or the 5 gigahertz band, and we take that range of frequencies, the channel that we're on, and we chop it in to different sub-channels, and we carry different conversations on those different sub-channels. Another type of multiplexing is time division multiplexing, and this one reminds me of Whitney Houston. To paraphrase Whitney Houston, with time division multiplexing, each conversation gets one moment in time. It gets its own time slot to send its data. Take a T1, for example. With a T1 circuit, you've got 24 different time slots, and maybe you could have 24 different conversations going at the same time, and there's going to be a little slice of time where conversation 1 can transmit, the next slice of time conversation number 2 can transmit, and so on. And that's a look at some of the different things that happen at the physical layer. So let's go up in our model a little bit. Let's add on now layer 2, the data link layer. What goes on here at the data link layer? Well, the data link layer is actually broken up into 2 sublayers There's the MAC, or the Media Access Control sublayer, and there's the LLC sublayer. The MAC sublayer is concerned with the physical addressing of a networking device. The common thing we think of, or the common thing I think of here at the MAC sublayer, is the MAC address that is burned into all of our network devices. For example, there's probably a sticker on the back, there is, that tells me the MAC address of this network interface card. It is globally unique. There's not another network interface card in the universe that has the same MAC address. It's a 48-bit address that makes this card unique from every other card in every other device. That's defined at the data link layer. And something else happening at the MAC sublayer is the logical topologies. Remember when we talked about token ring, we said logically we were circulating around a ring, but physically everything was starring off of this MAL. Well, the physical topology, that was layer 1, but the logical topology, which looks like a ring, that will be an example of layer 2. That's defined at the MAC sublayer. And one other thing we'll mention that happens at the MAC sublayer is the method we use to transmit data. And we've already given you an example of that. We talked about CSMA CD. Carrier sense, meaning we're going to listen to the wire before transmitting. Carrier sense multiple access, meaning that multiple devices can connect to the same media. Media access with collision detection. Well, the CD means that if there is a collision that happens, we can see that. If we have a hub, that's another layer 1 device that hopefully we don't have in our networks these days. But if we have a hub, the hub is going to send out a jamming message to all of the attached devices saying, hey, we had a collision. If we're physically on a bus, like I was back in, I guess, the late 80s, the voltage spike is going to be detected by the network interface card, and it knows that a collision occurs. So the method of transmission, that's defined at the MAC sublayer. Now let's check out some things that happen at the LLC sublayer. Well, at the LLC sublayer, we have connection services for one thing. That's going to give us flow control. If the sender is sending too rapidly, the receiver can say, whoa, slow down, you're sending way too fast. Error correction services or error notification services. The receiver might tell the sender, hey, I was expecting this data, I didn't get it, you might want to resend it. Something else happening at the LLC sublayer is the synchronization of transmission. So the sender and receiver, they're agreeing on when the bits start and stop. This sounds a little bit like layer 1. Remember, some features can show up in more than one layer of the OSI model. But an example of synchronizing transmissions between sender and receiver, one example is isochronous communication. With isochronous communication, both the sender and the receiver, they reference an external clock to determine these different time slots. Another type of synchronization is asynchronous synchronization. This is where the sender and the receiver can have their own internal clocks they reference, but they can send extra bits like start and stop bits to tell the receiver, here's when this transmission starts, here's where it stops. And with synchronous communication, we can have another channel between the sender and the receiver that's running a clock signal to say, here is one time slot, here is the next time slot. And at this data link layer, we typically think of Ethernet switches. An Ethernet switch, such as this is not a multi-layer switch. We'll talk about that in a second. This is a layer 2 switch. We've got these ports in the front, and we can connect printers, PCs, our regular network devices. They can use one of these RJ45. We'll use that term liberally. We'll use the RJ45 connector, and we'll connect into that Ethernet switch. And the switch is going to learn the MAC address of the network interface card on the other end of this cable. So if this were plugged in like this and this were powered on, the MAC address, as we transmit it into the switch would know that the MAC address on this card lived off of this particular port. So if somebody sends a frame, remember bacon frying produces salivation, frames at layer 2. If somebody sends a frame destined for this MAC address, this switch says, oh, I've seen that before. I made a note of that. I learned that that MAC address lived off of this port, and it will send the transmission just out of this port. Now that's an example of a layer 2 switch. Before we go on to layer 3 though, just be aware that there is such a thing as a layer 3 switch, sometimes called a multi-layer switch. That's what we have here. This is a Cisco Catalyst 3560 switch, and this is a multi-layer switch. In other words, it's going to be able to do some layer 3 and higher functions. We're going to see in a moment that at layer 3, we can make forwarding decisions for our packets based on destination IP address information. This can too. But let's take a look now at layer 3. Let's add that on as we're building our 7-story office building. At layer 3, we have the network layer. And the network layer is responsible, for one thing, for logical addressing. We had physical addressing in our network interface card, but logical addressing, that would include things like IP version 4, IP version 6. And back in the day, when I used to work at a university maybe 25 years ago, we actually routed not just IP version 4, we routed Novell's IPX protocol, we routed the Apple Talk protocol. It wasn't just IP. It wasn't clear that IP was going to be the big winner out of all those different protocols. I remember the day where there was the prediction that Novell's IPX protocol was going to be the de facto standard for networking. Didn't work out that way. And the OSI model was developed when we didn't know IP was going to be the winner. That's the reason we have some very non-IP-ish things going on here at the different layers of the OSI model. Now at the network layer, this is where we think of having routers. And we've got an example here of a Cisco 2911 router. And the router has a series of ports. I won't flip it around because it's really, really heavy, but it's got some ports on the back that we can connect out to our switches, which could then go out to our end devices. And the router, it's going to make forwarding decisions based on IP address information. The router is going to learn what IP addresses and specifically what networks live off of different interfaces. So if a packet comes in, remember packet at layer 3, if a packet comes into that router and it's destined for a particular IP address, the router can say, let's see, do I have a network in my IP routing table that would contain that IP address? If I do, I know to send this packet to the next hop router identified in my IP routing table. That's one of the things happening here at the network layer. Something else happening at the network layer is switching. Now, I'm not talking about layer 2 switching here. We're not talking about Ethernet switches. We're talking about things like packet switching. The act of routing is technically called packet switching. We're making a forwarding decision or switching the packet from the incoming interface over to the outgoing or the egress interface. And something else happening here at the network layer is connection services, such as flow control. And I know we've already talked about flow control at another layer. This is another example, though, of how a similar service can reside at multiple layers of the OSI model. Now, let's take a look at layer 4, our transport layer. And at layer 4, the two primary protocols I want you to be thinking about are TCP, Transmission Control Protocol, and UDP, the User Datagram Protocol. TCP is considered to be a reliable or a connection-oriented protocol. Here's the way it works. If you and I want to communicate using some sort of TCP protocol, we're going to go through a 3-way handshake to establish that communication. Here's what I mean. I'm going to send you a message saying, hey, I'd really like to chat with you. And that message is called a synchronization or an SYN. We pronounce that a SYN message. I send you a SYN, an SYN message. You get that and you say, oh, Kevin wants to talk to me. Cool, I'll talk to him. So you send me an acknowledgement for that, an ACK, an ACK message. And you also want to talk with me. So you send me your synchronization message. So I send you step 1, I send you a SYN, you send me a SYN-ACK, and then I want to acknowledge your SYN, your synchronization message to me. So in return, I'll send you an ACK, an acknowledgement. So again, the 3-way handshake. The first step is the SYN, step 2 is the SYN-ACK, and finally we have the ACK. Now UDP, that's considered to be a connectionless or an unreliable protocol, which begs the question, why would you want to use an unreliable protocol? And the answer is overhead, honestly. For example, think about voice and video going across your network. We're going to be using a protocol called RTP, the Real-Time Transport Protocol, which by the way is another layer 4 protocol. It's encapsulated by UDP, which also lives at layer 4. And the reason we use UDP is that it has much less overhead. We're not taking up as much bandwidth to send a particular video or voice packet. And if we did happen to drop the occasional video or voice packet, it's not going to be noticeable much, if at all. And we certainly don't want to say, oh no, we dropped this one, let's send it now. We don't want to receive video or voice packets out of order. That would look and sound kind of silly. So UDP, that's a great fit for some applications, such as voice and video. Now something else happening here at layer 4, the transport layer, is windowing. This says how much data can I send at any one time before expecting an acknowledgement. Take TCP for example. After that three-way handshake is over, the sender might send a single segment and it's going to sit there and wait for acknowledgement. The receiver hopefully gets it and they'll send an acknowledgement that says, okay, got it. I got segment 1. I'm acknowledging you saying I want segment 2. And we think, well, that worked pretty well. Instead of sending just one segment, it would be more efficient if I sent 2 segments. And then I wouldn't have to be spending all these periods of time waiting. So now I'll send segments 2 and 3, and I wait. I get the acknowledgement saying I'm ready for segment number 4, and I think, well, this is going great. I sent 1, then I doubled up, and I sent 2. Now I'm going to double up again, and I'll send 4 segments, and we send 4, 5, 6, and 7. And as long as we get successful acknowledgements, we're going to keep doubling up every time. We're going to go from 1, 2, 4, 8, 16, 32, 64, 128, 256, and on and on and on. But that's an example of windowing that TCP does. Something else happening at the transport layer is buffering. Let's say that the router is receiving traffic maybe from a gig link coming in from the local area network, and it's trying to send it out to the internet, which is only a fast Ethernet, a 100 megabit per second link. That's a 10-to-1 speed mismatch. What the router is going to do is it's going to take that data that it cannot send right now, and it's going to try to store it temporarily in a buffer area called a queue on the egress interface. And hopefully that interface is not going to fill up, its queue is not going to fill up. If it does, if we try to put a packet into a queue and it gets dropped because the queue is full, that's something called tail drop. We don't want that to happen. If we do, we have to retransmit our TCP packet, or if it's UDP, it's going to be lost forever. So we hopefully are going to have enough queue space to do that buffering. But buffering, that's something that happens here at layer 4. And we can actually influence using a series of tools called quality of service tools or mechanisms. We can influence how we empty that queue using the things like low latency queuing or class-based weighted fair queuing, so we can manage or we can influence who gets dropped and who gets through. And those are some of the things happening here at the transport layer. Next, let's move up to the session layer. The session layer is responsible for establishing, maintaining, and then tearing down sessions. For example, as we're establishing a session, we might be exchanging the parameters that are going to be used during the session. I do a lot in the unified communications world, and as we're setting up a voice phone call, we're going to be negotiating things like what port numbers are we going to be using? What UDP port numbers are we going to be using for RTP? What codec, what method of encoding voice are we going to be using? Those parameters that we're negotiating, that's all happening here at the session layer. And when we maintain a session, that's where we're talking about making sure that things are not getting dropped. If a connection drops, it's going to reestablish that session. And when we tear down the session, that's where both parties or all the parties in the conversation, they agree on, all right, we're stopping communication now. And they all agree to tear down the session. Let's move up to the presentation layer, layer 6. And one of the things happening here at the presentation layer is data formatting. For example, you've got a graphic image, a JPEG image. That is an example of something at the presentation layer. There's a standard for how JPEG images are constructed, or text might be in the ASCII format as an example. Something else happening at the presentation layer is encryption. We want to make sure that for security reasons, if I send sensitive information across the network, if it's intercepted by a malicious user, we don't want them to be able to interpret that information, so we can use encryption to prevent that. That's an example of something happening here at the presentation layer. And finally, one of the most misunderstood layers of all is the application layer up at layer 7. And I say it's misunderstood because a lot of times when we use the term application, we might think of an app that runs on our phone or on our computer. For example, think about Microsoft Outlook, if you use that for email. You might think, well, that's an application. Does it live at the application layer? No, it's not the program. That's not what we're talking about. The application means the underlying service that supports Microsoft Outlook. For example, the Microsoft Outlook protocols might include POP3, IMAP4, SMTP. Those are protocols that live up at the application layer because they support the feature of email. And as another example, think about a terminal emulation program that you might be using to connect into your router. Well, if you do that, you're using maybe Secure Shell as the underlying service, Secure Shell, that would live at the application layer, not your terminal emulator application itself. And you might argue that, oh no, Secure Shell, doesn't that live at layer 4? No, it's dependent on things happening throughout this layer. It does use a port 22 that's defined here at layer 4. It's using TCP port 22, but that doesn't mean it lives at layer 4. It's just using that particular feature at layer 4. But Secure Shell itself, it's going to live up here at the application layer. And one other thing happening here at the application layer is service advertisement, where a device on the network that wants to offer a service lets other network devices know about that service. The first example that comes to mind is Apple's AirPrint service. On my iPhone, if I want to print something out, I say I want to print, and it has discovered over the Wi-Fi network in my home, it's discovered a couple of printers that we have. Now these printers, they're compatible with Apple's AirPrint. They're actually sending out messages saying, hey, I'm this type of printer and I'm available over the network. And my iPhone sees that and I can print to that advertised resource. Well, the act of doing the service advertisement, that also lives here at the application layer. And that's a look at our 7-layer OSI model. Again, it's a reference model, it's not a reverence model. Not everything, not every protocol or device is going to fit neatly into one area. You might be spanning a couple of areas. You might use only one of the sublayers at the data link layer, for example. But it's just a way to better communicate about what's happening on our network. And that's going to wrap up our look at the 7-layer OSI model. If you enjoyed this video, please do me a favor. Please click the like button down below and subscribe so you don't miss any of our weekly content. Thanks a ton for joining us. We'll see you next time.